Hey everyone, welcome back, and today let's solve Leetcode problem 165 titled Compare Version Numbers. So we're given two version strings, version 1 and version 2, and we have to simply compare them, where a version string consists of revisions separated by the string dot, or period, if you will. The value of the revision is its integer conversion ignoring leading zeros, and to compare version strings we have to compare their revision values in left to right order. If one of the revision strings has fewer revisions, we have to treat the missing revision values as zeros as default kind of placeholder values, and we have to return the following. If version 2 is greater than version 1, we have an output of -1 to return. However, if vice versa, it would be an output of 1. Otherwise, if they're both equal, we'd return an output of 0. So in example 1, we have a version 1 to be 1.2, or 1.2 more specifically for this example here, and version 2 to be 1.10. In this case, version 2 is bigger, right? And so we'd have to return -1 because version 2 is greater than version 1. Let's go ahead and see why that is. And the first kind of revision value here, both of them are 1. So we just move on to the next revision because they're both equal. However, in the next revision, after this period here, or this dot, we see that version 2 is equal to 10 and version 1 is equal to 2. Since 10 is palpably greater than 2, it has a larger value. Version 2 is greater than version 1, and so because of that, we use this property here in the example, or the input constraints here, and so we'd output -1. Following the same kind of logic for examples 2 and 3, they're both actually equal to each other, right? 1.01 for version 2 and 1.001. The reason why is because they consider 0, 1 to be equal to 0, 0, 1, because these leading zeros really don't actually do anything. Like, they're both just really 1, and the same logic really holds true for example 3 as well, right? Because even though the length of this is only 2, the problem actually tells us that for any values, let's go ahead and see where this is. We have, for any missing values in the strings, we just treat them as zeros. And so we have to actually sub in the last two values to make this a length of 4 as zeros as well. And so both of these are still 1.3 zeros, right? So for the constraints here, we see that the length of our two version strings are going to be between 1 and 500, which are actually rather small for general input constraints and Leetcode problems. And both of these versions are only going to contain digits and the actual dot, kind of just confirming what the problem statement said. We're always going to have valid numbers, and it can always be stored in a 32-bit integer, and so we're not going to have any integer overflow or any issues like that. Kind of just confirming that we're always going to have valid inputs, if you will, according to the problem constraints, and kind of just confirming what the problem example and constraints actually told us. So this brings us to the main kind of way and solution and the key observation that we really need to make to be able to solve this problem in the most efficient way possible. Right now, at first glance, you may be thinking, well, this is a really simple problem. Like, why is it even a medium problem? Like, really, all we have to do is just compare the strings. But that leads us to that main observation, is that comparing the strings is not enough, right? It's just simply not going to work. And kind of tying that back to example 1 here, we can't just compare 1.10 and 1.2, because if we convert them to plain strings, we'd get 2 and we'd get 10 for these guys, right? And what's very important is that as plain strings, 10 would come before 2. And so we have to actually use kind of a numeric piece-by-piece comparison, as we wouldn't always get accurate values if we just convert this directly to strings like 12 and 110, or like 10 and 2, right? We need something a little bit better than that, right? Because, again, kind of tying back, 1.10 is actually greater than 1.2, right? As plain strings, though, 10 would come before 2. And so we'd have to actually get a numeric kind of piece-by-piece comparison for each dot, right? Which brings us to how we actually solve this problem, which is still rather simple, at least relatively. We're just kind of breaking this up into different pieces according to when we actually encounter dots. And the way we do that is actually using something called dot split in Python, and I'll explain more of that later. Let's first actually get into the kind of overview solution of how this is going to work. Effectively, the way we're going to use that split is basically just to split each version input string by that actual dot parameter, or input like period character, and basically that's just going to give us two lists of numeric chunks. And then from there, once we actually split them into numeric chunks or lists, we then iterate through both the lists at the same time, and at each position that we iterate over, we simply just compare the integer value of that specific chunk, or of that specific piece, if you will, from version 1 with the piece from version 2. Now, if any list is shorter, like the problem says, is we simply just treat those missing pieces or those missing chunks, if you will, as 0. And why that's so important is a good example is example 3. Versions like 1.0 and 1 are still going to be considered equal, because for that missing kind of revision value in 1, it would simply just be a 0, and so it would just be 1.0 as well, and so they would be also actually equal, right? That's kind of like the main observation that you really need to make as well. So let's go ahead and get into how we actually implement this in actual code. So the first thing that we're going to do is actually use that split method here, or that split kind of function in Python. And I'll just quickly type out the syntax for that and kind of explain how it goes. Let's just first try to find my mouse. And the way that's going to work is I'm going to call it v1 parts. You can call it pieces or chunks, does not really matter. It just stands for version 1 parts. And it's going to be version 1, which is our input 1 string, and we're going to pass the split method on it, passing in a parameter or an input, and I'll use this, as the actual dot, right? Basically, this is just going to split version 1 by this dot here. So every time we see this dot, basically what the split method does is it splits it into individual lists from the left side of the characters and the right side of the characters of each dot, right? So if we split like 1.0.3, that would split this version 1 string into a list of the string 1, the string 0, and the string 3. All right, so kind of just commenting that out in an example here. Example for 1.0.3, this would go to the list of the string 1, the string 0, string 1, the string 0, okay, and the string 3, right? And we don't need this comma. Right, now we're going to do the same exact thing, but for version 2. So I'm going to call it version 2 parts here, just to keep it as intuitive as possible. And you guessed it, it's going to be version 2.split, passing in the same exact parameter of that empty period, or that dot, if you will, right? Simply just doing the same idea for version 2. So this just creates our 2 parallel lists that we can now compare with each piece, kind of piece by piece or iteration by iteration as we iterate through both the lists. But before we actually start iterating, we first have to actually make that key observation of treating those missing values and finding which list is actually longer for our bottleneck iteration value, right? So I'm going to get my n value, and I'll explain this shortly. And it's going to be the maximum of the length of our 2 strings, or in other words, the length of our 2 lists of parts. It's going to be the length of v1 parts and the length of v2 parts. And why is this so important? Well, keep in mind, we're actually iterating over these 2 kind of lists here. And so we need to know how many iterations to actually make. For example, if we have this string here, 1.01, or rather not this one, 1.0 and 1.000, we can't just iterate over this 2 times because the length of version 1 is 2, because then we'd be missing out on the other comparisons of these last 2 zeros here from version 2. And so we have to take the longer string and use that as our bottleneck kind of iteration number. And so if we use a longer string, not only would we cover all the digits from the longer string, for any missing potential values or revisions values from our shorter string, we can just use them as default zeros, so we don't actually miss any characters or miss any comparisons. That's that kind of main logic here, right? We have to actually get all the possible values from our kind of longer version string, right? And so we have to take that maximum length n to know how many times exactly we have to actually loop, where all the missing parts will simply just be kind of treated as zeros, which now brings us to the actual iteration part once we actually handle that. And here, now we can very confidently just go for I in the range of n. That's going to tell us how many iterations we do, because that's going to help us cover all the characters from the longer string, right? To kind of just loop up from I equals 0 up to n minus 1, just letting us compare each chunk or piece position iteration by iteration. Now, how are we going to actually do this? Well, let's first grab the piece from the v1 part, to the version 1 string. I'm going to call it num1, and it's basically just going to be the integer value representation, just converting it to an integer data type of v1 parts at this specific index. Now, one thing that's very important is, what if this is a missing value that isn't actually listed in the input parameter or the input string v1? And so if I is less than the length of v1 parts, otherwise, we'd simply just make it a missing value of 0, right? That's kind of the main observation here. We have to grab this ith part or piece of the v1 parts. If it exists is the key observation there, right? Then we have to then convert it, of course, to an integer, as we see here, if I can highlight correctly. converted to an integer. However, if I is actually beyond the end of the list, meaning I is not less than the length of v1 parts, we then have to actually treat it like a missing value and use 0 instead. That's how we actually handle those missing chunks, like we saw in example 3, right? For 1.0, once we got to indices 2 and 3 for the last two values, we simply just use 0 for our final two chunks from version 1 and use those values to compare. And very, very similarly, we're going to do the same exact thing, but for the version 2. It's going to be the same thing. It's going to be an integer of v2 parts at this index. Now, of course, that's only if this index is actually less than the length of our actual string. If it isn't, then that means we have to treat it like a missing value, and so we just simply set it to 0 if it's not the case, so else 0, right? Very, very same logic, identical kind of process, just replacing the 1 with a 2 on this line for the second input thing. Now, what if num1, the piece for this specific index in the first version string, what if it's greater than num2? Well, then what did the problem tell us, right? If the first chunk is bigger, well, then the problem told us very clearly that we want to return 1, right? Because version 1 is greater than version 2. And so if that's the case, immediately we just return 1. We don't do anything else. We immediately return 1. However, if num1 is less than num2, we immediately return -1. Again, because the problem quite literally told us to. And sorry, there should be num1, not nums2. Right? That's because of the second chunk is bigger. Now, if none of these conditions hold true, we'd actually return -1. That just means basically version 2 is larger, and so we have to return -1 immediately, right? And sorry, in fact, I already handled that up here. Sorry about that. Now, finally, once we actually finish this entire loop, what if we haven't returned 1 or -1 anywhere, right? What if that is a problem? Well, if we go through this entire loop for every single piece in the entire input string, and we don't actually return 1 or -1, meaning both the strings are always equal in every single piece covered in all the iterations, only then at the end of the loop would we then return 0, because that would indicate that the strings are completely equal, right? We finished the loop without returning anything. Every chunk or every piece in every single kind of individual piece from both input strings were perfectly equal, and so both of the versions are identical, right? And so that's why we return 0 at the end of the loop if we haven't returned 1 or -1 inside the loop, right? So unless I made any syntax 0, 0, there should be accepted. There should be a valid solution. So let's go ahead and verify that. Oh yeah, sorry, there should be return. I don't know why or how I misspelled return, but now this should be accepted, and now this should be a valid solution. And now, as you can see, this is really just about as efficient as you can get it to be. So on a high level, how are we going to be really solving this problem? Effectively, we're first just splitting every single version into different numeric segments, like we see in version 1.split here, in lines 3 and 5. And then we're simply just comparing them position by position or piece by piece. And the first time we actually find a difference, we return which string is actually larger based on their numeric piece values for that specific iteration. But if we never find a difference in any iteration or any piece in both of those strings, that means they're perfectly identical and we return 0, right? Kind of just mirroring how we humans think about version numbers. 1.2.0 is really still equal to about 1.2, but 1.10 is actually greater than 1.2, right? Although, it doesn't really intuitively sound like that. It still is. Which brings us to the complexity of the solution. So for the runtime complexity, quite, intuitively, it's actually big O of n plus m. Why? Because we're splitting each string exactly once, big O of n and big O of m for their lengths, and then looping through at most the total number of segments. And so the overall runtime complexity is going to be linear, corresponding to the size of our input, so big O of n plus m, right? Where n and m are the lengths of our version 1 and version 2 strings. And for our memory or space complexity, it is the exact same thing. It's also going to be big O of n plus m, a linear solution, because we're storing these split lists, which together is going to hold all the segments. And apart from that, we're only using like a few extra integers like v2 or like n and things like that, and like num1 and num2, but that won't actually affect our runtime complexity or our memory complexity. So it's actually going to be big O of n plus m or linear for both complexities, for the runtime and space. So if you guys enjoy this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.